Okay, hi guys. Right, so this is all about extension to multi-dimensions. I'm also going to be looking at when we've got PDEs which model different things in the same PDE, we can split up our PDE to make it easier to solve. Okay, so today we're going to be looking at what's called dimensional splitting, where we split PDEs via the spatial dimensions, and also we can also use what's called term splitting to do something similar. As I just mentioned, many real-world applications require multi-dimensional domain. Okay, so my particular area is fluids. Fluids behave differently if you look at them in a 1D or a 2D case. Okay, you don't get turbulence in a 1D case, for example. So we need to have a way of extending our solvers, where up until now we've just, for the most part, we've looked at one-dimensional solvers. So just solving for the spatial dimension x. We need to be able to extend that to 2 dimensions or more. You could have a 3D domain. And to do this, what we're going to be looking at is, I'm going to be looking at the advection equation, but extended to the y direction as well. So just to recall, that the advection equation is u with respect to t plus the velocity with times u differentiated with respect to x equals 0. Okay, well, I can add a further term for the velocity in the y direction as well. This is change in u over time plus the velocity in the x direction times change in u over space in the x direction plus the velocity in the y direction times the change in u over that y direction. So this is exactly the same as a one-dimensional advection equation, which you're solving if you do a lab sheet 4, with an addition of a y term. So we've got another spatial dimension. By the way, I've used the uppercase characters x and y in that subscript so you don't confuse them with the derivatives. So vx and vy are just the velocity in the x direction and the y direction. And we saw with the one-dimensional equation has an exact solution, well, so does a 2D equation. So if this is our initial conditions, so u is a function of t, x, and y. So when t is equal to 0, if we have initial conditions of a function f of x, y, well, the solution after time t is f of x minus the velocity in the x direction times t, and y minus velocity in the y direction times t. So just straightforward extension to that y dimension. Okay, well, what I'm going to do now is I'm going to derive a finite difference scheme to solve that 2-dimensional equation, and I've called this an unsplit scheme. Okay, so I haven't done anything with the PDE, I haven't split it up. I've got the PDE, and I'm just going to straightforward solving it. Okay, so the first order Upwind scheme we saw a couple of weeks ago. So what we do is we take a forward difference in time. So that's the first order forward difference in time. And for the spatial direction, we take a backwards difference in the x direction. Okay, so this is the first order Upwind scheme. We also have got another spatial derivative, and again, I take a backwards difference in the y direction. Take note that we've got the indices I and j. Okay, so I is for the x direction, so uij is our current node, ui minus 1j is our node to the left, okay, and uij minus 1 is our node to the sort of the south or just below it. Okay, so that's all we've done there is substituted 3 finite difference approximations in place of our derivatives. We rearranged to make this one the subject. After a bit of algebra, that's what we get. Okay, that's the first order Upwind scheme for this 2-dimensional advection equation. The accuracy of this scheme is first order in space, first order in time, first order in the x direction, and first order in the y direction. Stability, if I use von Neumann stability analysis, which is quite difficult for a 2D scheme, I won't ask you to do that. It's quite tricky. We get this. This is our maximum allowable time step. And this is a much more restrictive time step than the 1D case. Okay, so when we go to 2D, if we don't use a split scheme, we have to use a lot lower value of delta t. The lower value of delta t means more steps, means more work. Done a little solution here. So with the 1D case, we looked at a bell-shaped curve and we moved it along the channel. With the 2D case, I've just got the bell-shaped curve in 2 dimensions. And the velocity in the x direction, so this direction up here, is 1, and the velocity in that direction is 1, so it should travel in the diagonal direction. As you can see, after a bit of time, my sort of bell shape has travelled from about this point here up to that point. So that's the 2D advection solution. What I've done on the next slide is I've taken a contour plot. So this is what we call a surface plot, so it looks like a surface. This is a contour plot, so looking down on it, each of these lines are of line of equal value. Okay, so that's our initial sort of contour. And this is our contour after some time. Now what we can see is it's sort of spread out in that direction. Okay, that is a deficiency of the numerical solver, not a deficiency or not a behavior of the solution. So we've got a poor solution, and what's more, it's taken us a long time to get it because of a restrictive time step. So that was what I call an unsplit method. So we just took the 2D PDE and we just straight away we just solved it the same way as we would a 1D, and we came across a couple of problems. Now, operator splitting, what we can do is we split our PDE up into 2 PDEs, one in the x direction, one in the y direction. And we use a one-dimensional solver for each of those separate ones. So we use a one-dimensional, the x direction, and a one-dimensional in the y direction. Now, these individual schemes can be combined to give the solution to the full PDE. So you're splitting up a difficult problem into several easier problems, and you combine the solution and you get the solution to the difficult problem. What are the benefits of this? Well, they have much better stability criterion. So we have a lot less restricted value of our delta t with the split schemes as we did with the unsplit scheme. They're easier to code, they're easier to derive, it's all round just easier. But what we do need to make sure is that when we split it up, we solve it, but the solution we get is equivalent to the solution we would get if we didn't split them up. So there's no point splitting it all up, solving it, and then not getting an equivalent solution, because you're not solving the problem then. What we're going to be using is we're going to be using a slightly different notation for this chapter, and we're going to be deriving what's called a differential marching operator. Sounds a bit posh, it's not really, it's quite simple. All it is if you think about a time marching scheme, so you've got the solution at the current time, and you use your finite difference scheme to get the solution at the next time step. So this is your solution at the next time step. We're going to write it in the form of some operator, which I've called big L of delta t, times the current solution. So UTX is the current solution. This operator is applied to our current solution to give us the next solution. And this L of delta t, we derive it by expressing the time derivatives in the Taylor series by spatial derivatives. Okay, so if we take our standard Taylor series, there we have second order Taylor. We know it's second order because the highest power of delta t is 2, and therefore we have an error of big O delta t cubed. That's our Taylor series. And what I'm going to do is I'm going to use this operator notation here. So the u, the derivative of u with respect to t is the same as saying little delta t of u. So this is operator notation. This is essentially saying value, this is an operator applied to my value. So ut is exactly the same as little delta t u. Likewise, the double derivative is the same as the operator delta double t applied to u. It makes the algebra a lot easier writing it in that form. So therefore, if we take that Taylor series, instead of u of t, we have little delta t of u, and instead of u of double t, we have little delta double t of u. So that's just a little bit of changing notation. We haven't changed anything. We're not messing about with anything. We're just changing the notation. And it just makes the algebra a bit easier. Okay, so let's step through what we do. Okay, I'm going to have a look at the 1D advection equation. Now, how we've written it in the past is ut plus vux equals 0. So writing it in the form of a differential operator, we have little delta t u, so that's the derivative of u with respect to t, plus little delta x applied to u, so that's the derivative of u with respect to x, multiplied by the velocity equals 0. Okay, we can use that to give us, okay, what's delta t of u? Okay. The reason I've got this is if I go back a slide, I want to replace this with a spatial derivative. Okay, at the moment it's a time derivative. I want to replace it with a spatial derivative. So all I've done is taken that term, second term, over the other side. So that gives me the first derivative of u with respect to t. And what I can then do is, because I've got a second order Taylor, I need the second derivative with respect to u of t. So the second derivative of u with respect to t is the same as saying find the derivative of u with respect to t and then find its derivative again. But here, I already know what delta tu is. So instead of this bracket, I put in this right-hand side here. Okay, so what I want to write this derivative in the form of a spatial or an expression involving spatial derivatives. It doesn't matter which order we take the derivative in, whether we do derivative with respect to x first and then do it with respect to time, or whether we do it with respect to time first and then do it with respect to x. So if that's the case, I could just swap delta x and delta t around. And what we have is this expression. So minus v times little delta x multiplied, or applied to, I should say it's an operator, it's applied to little delta t u. I've also got a little delta t u there. So this bracket here can be replaced by that right-hand side. Okay. Multiply out the bracket. Okay, so I've got minus v times minus v. So that'll give me v squared. I've got derivative of u with respect to x, and then differentiated again with respect to x. So that's a double derivative. So on this slide, what I've done is we take the PDE and I express the first derivative of u with respect to time in terms of its spatial derivative just by rearranging the PDE. And I do the same for the second derivative. in time using this. Okay, so what that means now is I can replace my delta t's in the Taylor series with spatial derivatives. Oh, there's a slight, yeah, I was just messing about with these slides just now. There's a slight typo on the side. That shouldn't be a subscript X, that should just be a T. See if you got it in. So what I mean by that is, yeah, it's right in the notes. I'm just going to, okay. So just got a slight typo on the slide, but this is what I'm trying to show here. Okay, so that should be big delta T, little delta X. And that should be big delta T squared over 2, little delta X to the double derivative. So there's a slight typo on there, but it's okay in your notes. So just ignore that first line. Okay, what we do, factorize out all of our instances of U. So we've got one instance of U there, one U there, and one U there. So if I factorize those out, so the contents of the square bracket is the factors of U, okay, I get this. That square bracket is my LX, or my L delta T. So that is my marching operator for that infection equation. So this is what we wanted to find. We wanted to find this L of delta T. Okay, notice this is all in spatial derivatives. If I wanted to calculate a finite difference scheme for this, I just replace delta X by some finite difference approximation and delta double X with another finite difference approximation. And that will give me second order accurate in time. You've got to remember this is your error. So when we have delta T, you'd have delta T over the left-hand side underneath. So we divide that by delta T there. Okay, so this LX, or LX delta T, that's what we're trying to find. That's what we call our differential marching operator. That is applied to U in order to get our next solution. Okay, let's have a look at that in 2 dimensions. Okay, so the 2D infection equation is similar. Okay, so there's your U with respect to T, there's your U with respect to X, and we've also got a U with respect to Y. Okay, we do exactly the same. So moving both the X and Y terms to the right-hand side, we get our delta TU, and we also need delta double T. Okay, so we always use the fact that the second derivative is equal to 2 first derivatives. So differentiate U with respect to T, and then do it again, and we get the double derivative. Well, from the first one, this is our delta TU. So the bit in the bracket is replaced by that right-hand side. Okay, well, if we expand out the bracket, okay, remember the sum of the derivatives is equal to the derivative of the sum. So that's a derivative of the sum, so we can split them up and treat them separately. Okay, so you can see we have minus Vx delta x times delta t minus Vy delta y and delta t. This is also switch the orders of the derivatives. It doesn't matter whether you differentiate with respect to x or with respect to t first, and likewise with y. Okay, well this bracket, same as that bracket, we're just going to insert that right-hand side. Okay, so same thing again. And again, if we expand out those brackets, okay, so here we have minus Vx times minus Vx, Vx squared, derivative of x, applied to the derivative of x is a double derivative. Here we've got minus Vx times minus Vy. Okay, so we've got Vx and Vy, and we're going to have the same for this one here. That's where the 2 comes from. And we've also got Vy minus Vy times minus Vy squared. First derivative of y applied to the first derivative of y. It's a double derivative. Okay, so exactly the same as a 1D case. We just got 2D. You write it in the form of what is our derivative with respect to t. What does that equal? And then we also find the second derivative. If we really wanted to, we could find the third and fourth. But the algebra is just a bit too lengthy and boring for that. Okay, well, same thing as before. Let's sub it into the Taylor series. Okay, so this is it, subbed into the Taylor series. There's our u. Okay, the reason it's minus delta t, so just go back the slide, is because, why is it minus delta t? Oh yeah, there it is, yeah. Okay, the reason there's a minus is there's a minus there and a minus there. So just take that out. So that's the minus. That's delta t times the derivative with respect to t, is that one, plus delta t squared over 2 times double derivative with respect to t, which is that thing which we just derived. Okay, again, factorize out in terms of u. Okay, everything in the square bracket is our marching operator. That's applied to that value of u. Okay, so what we say is our next solution is equal to the marching operator applied to the current solution. And what I've done is I've written this as L subscript xy. That means it's 2D. It's taken both x and y into account. Okay, so, and that's our two-dimensional marching operator. What this means is, if we were to split up the problem, take our marching operators in the split problem, combine them, we should get something which is equivalent to that. If we don't, we've got a problem, we can't split it. So that's what that basically says. We need to combine marching operators for the split schemes, i.e. if we split them by dimension, to be equivalent to this. So in other words, Lxy of delta t should be equal to the combined. So this means we apply Lx first, and then apply Ly to whatever Lx is. Okay, so that's the idea of splitting. We can split by dimension, and we can also split by term. I'm going to first look at splitting by dimension. Essentially, this splits a PDE in n dimensions to n 1D PDEs. In other words, it just makes a complicated problem simpler. Combining the 1D schemes should provide the solution to the n-dimensional PDE. Okay, so let's have a look at the advection equation which we've just been looking at. In 1D, that's the advection equation in the x direction, and that's the advection equation in the y direction. So rather than solving the 2D advection equation, I'm going to solve two 1D advection equations, one in the x direction, one in the y direction. We've already seen that this is a marching operator Lx of delta t. So it follows that instead of wherever we see an x, if we replace that with a y, we have the operator in the y direction. Okay, no point doing all that work for that. Again, we'll just get that. So it's easy to see that. So if we combine these two, we should get that combined one, or the unsplit marching operator. These are the split ones. Okay. What does it mean in terms of the solution? Well, if you've got a 2D domain, so we've got a 2D domain, all these finite different nodes here. What we're doing is we're solving for lots of 1D problems in the x direction. So we do it like the x sweep. And then taking that solution, we do the same for the y direction. Lots of 1D problems in the y direction. That's easier to do than just doing the 2D solution. And that's solving it first in the x direction. So Lx is first applied to u, then whatever that result is, we apply Ly to it. Okay, so we've got to test whether we have that equivalence. So that's what we want to happen. That has to happen for us to be able to split it. Okay, so for the 2D advection equation, okay, the first bracket is your Ly, and the second bracket is your Lx. Okay, lots of algebra, not going to lie, can get a little bit tedious. But how I tend to do, how I've done it here is I take the 1 from the first bracket and multiply it by those 3 terms. Multiply it by those 3 terms. So 1 times 1, 1 times this term, and 1 times that term. So that's where those 3 come from. Then take the second term, times it by all those 3. So minus Vy delta t delta y times that. Okay, times it by that gives you that one. Times it by that gives you that one. And so on and so forth. So it's a fair bit of algebra. Okay, we've gone up to, we've got a few terms here which involve delta t to the power 4 and also delta 3 cubed. We don't need those terms. We're only looking for a second order. Okay, so our sort of order to error term is delta 3 cubed. So what that means is we can totally ignore anything which is delta t to the power 4 and delta t cubed. So we're truncating to second order, so it just totally wipe out those terms. Okay, which gives you this. So if I just wipe out those, I think we've done a couple of, yeah, so that just gives you that, which we could do a bit of factorization. Okay, so here we've got a delta x term, there we've got a delta y term, but both are multiplied by delta t. Okay, here we got half the x squared delta t squared times a double derivative. Okay, we've got vx, vy here, but because we're taking out a factor of a half, I have to times that by 2. And we've also got a double derivative of delta y there, which we see is equal to our unsplit operator. So you take your 2 split operators, combine them, you've got to make sure that they're equal to the unsplit operator. They are, so this means we can split the problem. Sorry?
You said ignore 2 cubed delta, but you've got it in Everton.
Where have I got it? Where have I got it here?
In Everton.
Oh yeah, that is the error term. So this basically means there are lots of other terms which involve delta t cubed and higher, but we've ignored. So it's kind of a
So for example, if you were to include them all, then you get 10 for example. If you did take them to the second order, you get 9 that all would equal 1.
sorry, if we.
It's basically the difference between the real one and the second order.
Yeah, well, it's the difference. Yes, exactly right. It's the difference between the exact solution and our approximation would be that. But because remember, delta t is a fairly small number, so delta t to the power 4 is going to be a lot smaller number than that. So we can just hide it. We can sort of push it into the error. So after all that algebra, we see, but this is indeed satisfied. So we have our unsplit operator is the same as 2 of our split operators applied. Okay, so how do we use this? Okay, so we showed we can split up our 2D problem into 2 1D problems. It doesn't matter which direction we solve for first. Okay, we can solve in the y direction first, then x, or x and y, it doesn't matter. I normally do x and y, habit, really. We can use different solvers in the x and y direction. You don't have to use the same one. Although this may affect the order accuracy. We normally use the same solver for both directions. Okay, so if we use the first order upwind scheme for both x and y directions, what we can do is we first solve in the x direction. You've got lots of different 1D problems you first solve in the x direction. And I've called that solution sort of superscript n star. That's not the full solution, that's like a halfway intermediate solution. What you then do, so after we solved all of our 1D problems in the x direction, you solve all your 1D problems in the y direction, but using the solution from the x direction problems. So notice these are all n stars here. Okay. Once you've done that, you then have to march forward one time step. Because we got two 1D sort of schemes, your maximum allowable time step must be the smaller of the separate time steps. Okay, so if you use a first order upwind scheme, you'd have delta x over the velocity in the x direction, or you'd have delta y over the velocity in the y direction. Whichever one of those is a smaller, that's your maximum allowable time step. It's a lot, that number's a lot bigger than the unsplit maximum allowable time step. So it's a lot quicker to split this up. I don't know what you're doing there. Okay, so what I've done, by the way, I'm not asking you to apply this. This is what I've done. Same problem as before. We had that 2D advection problem. Started off here. It's sort of velocity of 1 in the x direction, velocity of 1 in the y direction, so it's going to go diagonally across that domain. And after a while, you can see it's got up to that point there. If I have a look at the contour plot, that's a start, and you can see it's propagated up to about here. And what's more, you can see we've got circular contours. So we had a skewing when we had the unsplit scheme. By the way, I don't know why it was skewed. I'd have to look into that, but it was just not right. With the split scheme, we don't have that. So not only is it quicker, it's more accurate for this case. Okay. I'm not, like I say, I'm not sure why it got skewed. I'm going to have to sort of investigate that a bit further. Okay, so that's dimensional splitting. Yeah. Yeah, I do exactly the same. Yeah, so here we've got a surface. Imagine that's a hill. So all a contour plot is each of these lines are lines of the same height. So when you're looking down on it, not necessarily. The steeper it is, the closer your contour lines are together. So as you can see, that bit in the middle is the highest point. Okay, that corresponds to that bit there, looking down on it. Quite easy to do in MATLAB. Okay, so that's splitting by dimension. Okay, if you've got multiple dimensions, x, y, or even z, you can do it in third dimension as well. You can also do it by terms. And what I mean by this is you might have a PDE which models several different things. So you might have something that models the change in pressure across space. You might have something change in temperature, could be change in velocity. The heat diffusion, you can have something which heats up but also moves along. So you might have several different terms. And we can split it by these terms. Okay, and treat each term separately. So here's an example. This is what we call the advection diffusion equation. So if you ignore that bit for now, we've just got the advection equation by adding on a diffusive term. We saw that last week with the heat, modeling heat diffusion. So this equation here models not only heat diffusion, but what happens when that diffusion moves along. What we could do is use our standard way of solving it by replacing each of these with finite difference approximations, rearranging to make that the subject, and that will give us that scheme. And using von Neumann stability analysis, which we did last week, we see that was our maximum allowable time step. Actually, we didn't do it for this this equation, but if we did, and it's quite difficult to do that, that's our maximum allowable time step. Okay, it's a lot better to actually split these up. So that's our initial equation. I could write that as two. Well, actually, sorry, I'll derive the unsplit scheme first. Okay, so that's our initial equation. I could write that using operator notation by moving the spatial derivatives over to the other side. Okay, so that gives me my little delta t. And using the same process as before. So a double derivative is simply two single derivatives. Okay, well, we've seen from this one, that's our single derivative. So we replace the contents of the bracket there. Okay, sum of a derivative is equal to the derivative of a sum. So we can split that up. Doesn't matter what order we do the derivative. So I could swap the delta t with the delta x there and the delta t with the delta x there. Okay, and we have this sort of thing again. So again, plug that in. Okay, bit of algebra, and that's our second, that's our delta double t. Okay. Say exactly the same as what we did before. That's our single derivative with respect to t. That's our double derivative with respect to t, and we substitute that into the Taylor series. Okay, there's your Taylor series. Okay, so we now have an expression for that term and an expression for that term. So substitute them in, and we need to factorize out the u term. Okay, so the thing in the square bracket is just, okay, there's one u there, so that's where the 1 comes from. Okay, there's delta t times that bracket times u there, so that's where that comes from, and the last term. Okay, the contents of that square bracket is the differential margin operator for the unsplit infection diffusion equation. So I've called it LAD. It's not a lad, it's just AD is infection diffusion. Okay, that's the unsplit. We're going to split it up into one is going to be an infection problem, one is going to be a diffusion problem. Okay, you can do that. So there's our 1D infection, there's our 1D diffusion. I'm not going to go through all of this, but that's where we have the operators. And if we look at the marching operators, that's our infection marching operator, LA I've called it, and that's our diffusion operator, LD. Now we've got to check whether if we apply these two separately, whether it is the same as this unsplit one. Okay, so that's your LA, that's your LD. Okay, so expand out the brackets. Okay, lots of algebra. Simplify as far as you can, and you'll see that that is equal to the unsplit operator LAD. So the split scheme is identical to the unsplit scheme. Implementation, very, very similar to before. So this is we choose schemes. So I've chosen a first order upwind for the advection equation and a forward time central space scheme for the diffusion. So there's my first order upwind. Okay, and this solves for n star. So that's just solving for the first term. This isn't the solution, that's the sort of halfway solution or part way. And then we use our n star in our forward time central space scheme, and that gives us our solution to the whole thing. Now, when we looked at advection and diffusion separately, that was the maximum allowable time step for the advection equation, and this was the maximum allowable time step for the diffusion. So what you do is you calculate this one, you calculate that one, and you pick whichever's smallest. If you don't pick the smallest one, what it will mean is your scheme would be stable for one term, but not for the other. And if it's not stable for both terms, it's unstable. Okay, that's it says typo in notes. I think I might have fixed that. No, fix that. Don't worry about that. Okay, and this is sort of I've coded up that scheme to solve this. So this is the original red solution, and over time, what happens is it both moves along and starts to diffuse. I don't think there's a solution to this one, so I haven't plotted the exact solution. So remember, that's using a first order upwind scheme, which is first order, and a forward time central space scheme, which is second order. So it moves along, and it also sort of starts to diffuse. But the problem is first order schemes are diffusing. How do I know that diffusion there isn't a property of the numerical scheme as opposed to the equation? So what I've done here is I've used a first order Lax-Friedrichs, or actually not Lax-Friedrichs, it's first order upwind, and Lax-Wendroff, which is second order. So this is this solution here, the last sort of bell-shaped curve there. And just to compare them, and you can see that the red one doesn't have that as much dissipation. Okay, so you should probably have chosen a second order scheme for the advection part as well. And that's just something to be aware of. Okay, just going to talk a bit about stiff problems. Essentially what stiff problems mean is that your time step is really restrictive because of one term. Those of you who do ODEs will probably meet stiff problems in ODEs. But let's say we have a two-dimensional scheme, two-dimensional domain, and our time step for the x direction is a lot less than our time step for the y direction. So you can solve for the y quite happily using a larger time step, but x is being awkward, it requires a lot shorter time step. Okay, that's essentially what a stiff problem is. It's when one term is being awkward. Okay, so if we're using a split scheme, then we have to use the same value of delta t for both schemes. But what is quite nice is, let's say that our delta x tx was a lot less than delta ty. What we can actually do is apply lots of different operators in the x direction, then apply the operator in the y direction just once. Okay, which is the same as doing that. Okay, so let's say delta ty was equal to n times delta tx. So you do n lots of solutions in the x direction followed by one lot of solutions in the y direction. We have to show that's valid. So I'm just going to use the first order one, and it's without loss of generality. This proof also extends to n order n. Okay, there's the first order operator for the advection equation. Okay, and I'm going to say, okay, I'm going to use n lots of the x solution for delta t over n, followed by one lot of the y solution for delta t. Okay, there's one lot of the y solution, followed by, well, n lots of the x solution. Okay, use binomial theorem. Okay, remember, we've swallowed up a lot of the delta t terms in this error. Okay, do our multiplication, and we get to this, which happens to be the same as the unsplit. So this proves we can do this. Again, that's not something we're really worried about in this unit, but that's what we can do. A common splitting sequence is to use what's called strand splitting, and this is the dimensions. What we do is we solve for a half time step in the x direction, followed by a full time step in the y direction, followed again by a half time step in the x direction. So, often called a symmetric splitting sequence. Okay, and that's named after Strang, and that's quite popular. Okay, well, I'm going to finish off with a worked example. So just to finish off the chapter. There is a lot of theory here, not a lot of practice, but yeah, hopefully you're not finding it too difficult. Okay, so I've got this two-dimensional PDE. So I've got a single x derivative in in the x direction, and I've got a double y derivative in the y direction. So step one, derive the unsplit second order differential March operator. Okay, so the first thing I'm going to do is actually rewrite the equation using those derivative operators. By the way, I take it you're familiar with this Greek letter here. Lowercase delta. That's where D derives, the Latin characters for D derives from. Okay. Mine often look like S's, so just make sure you sort of finish the loop. Okay. So that's this equation, just written using operators. Okay, first step we need an expression for little delta t and an expression for little delta double t. So delta t, all I do is take both of those terms to the other side. There you go. There's my term for delta t. I also need delta double t. And as always, okay, a double derivative is simply the first derivative applied twice. So that's equal to, that's delta t, and then that's my first derivative, so I'm going to place that within the bracket. I can't write like that, I'm going to have to, yeah. Okay, a sum of a derivative is equal to the derivative of the sum. And also, it doesn't matter which order we take derivatives. So what I'm going to do is I'm going to split this bracket up, and I'm also going to swap the order of the spatial derivatives with the time derivative. So what we end up with is, okay, so that's the first term, simply a t. So that's minus alpha times the spatial derivative times the time derivative. We also have minus beta, spatial derivative times time derivative. Okay, well, here, both of these brackets is this term. Okay, so what I'm going to do is I'm going to replace what's in the bracket with this term here. And that's applied to minus alpha delta x u minus beta delta double y u. And I also do the same for the second one. All I have to do now, expand out, simplify, and I get my delta double t. So what we're going to get minus alpha times minus alpha is alpha squared. And that's multiplied by the second derivative of u. I'm going to have minus alpha times minus beta, and that's going to be multiplied by delta x yy. If I look at the second one, I'm also going to have a minus alpha times minus beta times delta x yy. So what we have here is plus 2 alpha beta, and we have a mixed derivative there. Okay, so I've probably missed out a step there, but it's not too difficult to see where that comes from. Plus beta squared. Okay, and then we're going to have a quadruple derivative here, because there's a double derivative in terms of y. Oh, yeah, double derivative y there applied to a double derivative y there. So quadruple derivative. Okay, so that is our initial unsplit equation, and from that we have our expression for delta TU and our expression for delta double TU. Right, now we use a Taylor series. Okay, so if I write out the Taylor series using those differential operators. Okay, so I have an expression for that term, the delta TU, and I have an expression for that term, which is delta double TU. So we have U plus delta T, okay, and we have, this is our single derivative. Plus delta T squared over 2 times our double derivative, which we'll probably run out of space here. But okay, don't know whether that makes sense. That's the fourth derivative. Okay, factorize out in terms of U, and what we end up with is I've got 1 times U there, that's 1. Okay, I've got this times U, that's delta T minus delta X minus, sorry, that's should be alpha delta X, shouldn't it? Yeah, I've missed out an alpha there. Minus beta delta YY plus dt squared over 2 alpha squared delta XX plus 2 alpha beta, and I've also missed out something here. That should be a delta X YY there. Oh, run out of space. And that's all times by U. Okay, I should have left myself more space than that. So all that line is that line, but with the U's factorized out. So therefore, I'm going to start way over on the left here to give me more space. The unsplit marching operator, so LXY, is equal to the contents of that square bracket. Oh, no bracket there. Should have been bracket, should have just been around the bracket. Okay, that's my unsplit operator. Lots of algebra, okay. But if we do split up this problem by dimensional splitting, we've got to make sure that our product of our 2 split operators is the same as that. Sorry? That line.
Yeah. You know the very first bit where you
That.
No.
Why you took the U out?
Yeah, you change U to 1.
Yeah, I'm just factoring it out U. So there's one lots of U there. Here, but remember these are operators. So this is going to be applied to U. So we have an operator there which is just times by 1. So that's my operator there, times by 1. Here we've got delta t minus alpha derivative of U. Okay, so that's the same as saying delta t minus alpha derivative, and that's applied to that U there.
So that U that you put there, is that?
Yeah, all of that
Yeah,
is applied to that.
That makes sense.
Sorry, I should have kept it on the same line, but ran out of space.
So I can put it at the front as well.
You can actually, yeah. No, you can't actually, no, because an operator appears before the thing is being applied to. So when we say times by 2, you don't say 2, you can't say 1. If you times 1 by 2, you do 1 times 2. You don't do 1, 2 times.
Yeah, I get
So,
it.
yeah.
So you basically taking U out the whole thing.
Yes. You's just taking it out. I want to strip you out of it, so I've just got the operator.
Oh.
Okay, so that's the unsplit marching operator. What I'm now going to do is I'm going to split the PDE, have a look at what these split operators are, and just check whether if we combine those split operators, we get this, which is what we want, because then we can split the problem.
So you know, on that third line, you're saying you put the U out at the end.
Yeah.
You haven't put it on there.
Yeah. Essentially, what I've written this as is I want U. My next value of the solution U is equal to LXY delta T applied to U. So
that's what the left hand
Yeah.
side means. Is that what you mean?
yeah, that there is essentially saying what's my next value, what's my next solution. And that is equal to this operator. All of that is applied to my current solution. Okay, right. The next step is use dimensional splitting to split the 2-dimensional PDEs into 2 1-dimensional PDEs. This is easier than you think.
Is that on the first bit?
Sorry?
On the first part?
Okay, so we had UT plus, and I've forgotten it already, alpha UX plus beta UYY equals 0. Okay, that's my unsplit equation. That is the same as UT plus alpha UX equals 0 and UT plus beta UYY equals 0. Make sense?
So do you want to flip it backwards?
Sorry.
Just 1 second. Okay, yeah. I get it.
Okay. Okay, so there's our 2D one. That's 2D. That's 2 lots of 1D. So rather than solving a not 2D. Oh yeah, rather than solving a 2D problem, why not solve 2 1D problems? It's easier. Okay, so that's part 2 done. Well, easy as that. Part 3, derive 2 second-order differential Martian operators for each of these split PDEs. Okay, so for the first one, so I'm going to call that equation 1 and that equation 2. Okay. So write it in the form of a differential operator. UT is the same as delta TU. Take that term to the other side, so I have minus alpha. Oh, no! God damn it. Almost. Balls up there. Okay, and then there's the x derivative. Okay, so that's your delta t. You need delta double t now. So a double derivative is just simply a first derivative applied twice. And from the first equation, we see that delta t u is minus alpha delta x u. Swap the order of the derivatives around. You can do that. And again, we replace the delta t u with minus alpha delta x u. Okay, and therefore we have alpha squared times delta x x u. So this is for the first equation, equation 1. That's our first order derivative with respect to time. That's our second order derivative with respect to time. So we replace our derivatives in the Taylor series with those two. So again, using Taylor series. So we've got Taylor series is u plus delta t times the first derivative. So I'm going to go straight ahead and just plug that in. Plus delta t squared over 2 times the second derivative. Take the u's out. So I've got one lot of u there, plus delta t times minus alpha delta x, plus delta t squared over 2, alpha squared delta double x. And that's all applied to u. Contents of the square bracket, that's your marching operator. So essentially all we've done is taken the Taylor series, taken our PDE, and replaced the time derivatives in the Taylor series with the spatial derivatives from the PDE, and that gives you your marching operator. Okay, so that's our operator in the x direction. We've also got to find one in the y direction. Okay, so we've also got to do the same for equation 2. Being a bit lazy here. If you do all of that step down to there for the second equation, that's what you get. I mean, you could fill in the blanks there. I haven't got much space on the bottom of my page, so that's why I've been lazy. So for that one here, do exactly the same as this, but for the second equation, and you'll get this. Is that sort of do you mind me missing all that out? Just algebra. Okay, so we do the same as we did here for the Taylor series. But this is for the y direction, so we've got u plus delta t times the first time derivative. Okay, plus delta t squared over 2 times the second time derivative. Oh, that's applied to u. Again, factorize out u. So that gives you your operator in the y direction. Okay, so Lx, that's your sort of operator, that's what we're doing in the x direction. Our y is what we're doing in the y direction. If we combine those two, they should be the same as Lxy, which we did over the page. We've got to show that because you can't go ahead and use a split scheme unless you know you're getting the same as an unsplit scheme. You're just wasting your time. Let me know when I can turn the page. Okay, if you've already written all that down, try and go ahead and multiply this by that, see what you get. Okay, so that's what we're going to do now. We're going to combine those. I'm just going to turn over. Right. So what I'm going to do now is work out what the combined operators are. If I do the split, if I solve in the x direction, then in the y direction, what's the product of that? So the operator in the x direction is this. And that's followed by, so it's going to be multiplied by the operator which we just had a look at in the y direction. So all you got to do is multiply those two square brackets together. You can be posh, you can do it in flash ways, but I like to do sort of methodical. Take the first term in the first bracket, multiply it by the second bracket, etc. So 1 times the second bracket is just the second bracket. Then I'm going to have delta t times minus alpha delta x, all times by the second bracket. This term here, okay, that was this term multiplied by that one. So delta t times delta t gives me delta t squared. Minus alpha times minus beta gives me plus alpha times beta. And then the derivative in the x direction applied to the double derivative in the y direction gives you a mixed derivative delta x, y, y. And then it's this term multiplied by that term. Minus alpha beta squared delta x and then 4 y's. Okay, so that's the second term in the first bracket multiplied by all of the second bracket. Lastly, the third term in the first bracket multiplied by all of the second bracket. So we've got delta t squared over 2 alpha squared delta xx plus delta t cubed over 2 minus alpha squared beta delta x, x, y, y. Okay, so a double derivative in the x direction applied to a double derivative in the y direction gives you a mixed derivative x, x, y, y. Okay, and then it's this term times this term. That's delta t to the power 4 divided by 4. Alpha squared beta squared delta x, x, y, 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 y. You may be asking why we do all this. No one ever laughs at my jokes. It's just sad, isn't it? Right. Okay, lots and lots of algebra. Let's cancel stuff out. Well, the first thing I'm going to do is anything with a delta t to a power greater than 2, I'm going to cross out. Because we're only looking for a second order operator sequence. So that means I'm going to get rid of that one. I'm going to get rid of that one. And I'm going to get rid of that one. Okay? Because they're all going to be swallowed up by my big O delta t cubed. That's all swallowed up in that error. Okay. Now I'm going to factorize by delta t. So I've got my 1. That's on its own. So that's my 1. Yeah, because the reason being is here I only took it up to the second. I could have gone for delta TTT, but we'll probably still be here writing down that. But I've gone up to second order. So anything which delta t cubed and above, with its r, that is smaller than our error.
So if you would have got TTT, you would have gone T to the 4. Yeah.
Do you really want? You could go there if you want. Let's not go there. Okay. So what I'm going to now do is factorize out for delta t. So here I've got delta t, which is minus alpha delta x, and I've also got a delta t times minus beta delta yy. So that's that term's taken care of, as is that term. And I'm also going to take delta t squared over 2 and find its factors. Okay, well, we've got a delta t squared over 2 there. That's alpha squared delta xx, that's that one. And what we've also got is we've got this one here, but this one hasn't got a factor delta t squared over 2. It's just delta t squared. So if we times this by 2, when we halve it there, we get back to what we started with. Okay, so this one has to be times by 2. You get why that is? Yeah, I've taken out a factor delta t squared over 2 because that isn't over 2. I multiply that by 2, then halve it and get back to where we started. Okay, and the last one is beta squared over the quadruple derivative. Okay, so that's my split operator sequence applied. That gives me that as my combined. What we wanted that to be equal to the unsplit operator sequence. Okay, so drum roll please. Okay, then. We wanted that to be equal to this. That one there. Let's have a look. Just checking it. Yep. Hey! I'm glad that worked because that would have ruined the whole lecture. And we're happy. We're happy because we've shown we can split up our problem. You're not happy? Would you rather solve one hard problem or 2 easy problems? 2 easy problems, so therefore we can do that. Okay, so that's splitting. You're not going to be asked to sort of apply that in terms of write any programs or anything in the assignment. In the exam, you may be asked to prove that a sequence is a split sequence is valid, and then you have to essentially go through this step. Just a lot of algebra. It's not too sort of tricky.